Hello guys, in today's video we will see about the duct design and solve a numerical based on the duct design. So basically we will see what is the duct, what is minimum duct design, what are the different types, what are the different methods of duct design. Actually duct design is to find the suitable dimension of the each branch of the duct. That is simple definition of duct design. We will see. The object of duct design is to determine the dimension of all the duct in the given system. The duct should be carried the necessary volume of conditioned air from the fan outlet to the conditioned space with the minimum friction and dynamic loss. That is the basic motive of our duct design. Then the area change must be gradual and limited to not be more than 20 degree for diverging and 60 degree for the converging area. Though when the area changes of the duct, that should not be that should be between the 20 to 60 degree and should not cross that limit. For the rectangular duct, the aspect ratio of 4 and less is desirable but should not be greater than the 8 and in any case. So aspect ratio is basically what? The ratio of length into breadth. So that should not be greater than the 8 sorry, that should not be greater than the 4, and it's better to having less than the 4, but in any case it can be in between 4 to 8 but not should not be greater than 8 in any case. The minimum sheet metal is required for required with the square cross section for the given cross sectional area. So that are the basic parameters and basic steps for the duct design. Now we will see the methods. There are three main methods: velocity reduction method, equal pressure drop method, and static regain method. Mainly we use the equal pressure drop method in our case. So we will see that one. Equal pressure drop or frictional loss method. So what is it? We will see. In this method, the size of duct is decided to give equal pressure drop or friction loss per meter length in all the duct. Here in all the duct, pressure loss is remain same. So basically uh, for the for taking the same pressure loss, we should have to design that particular dimension or select the duct. If the layout of the duct is symmetrical, giving the same length of the various runs, this method gives equal pressure loss in various branches, and no dampering is required to balance them. Now, in case of the run are the different length, then the shorter run will have minimum loss and consequently higher pressure at the outlet. It is therefore necessary to reduce the higher pressure by heavy damping or modifying this method proved higher velocities in shorter runs. But the higher velocity shortened run may create huge objectionable noise, thus noise absorbing outlet and fitting must be provided. So to provide the equal pressure drop, the velocity should be maintained properly. In the shortest run, velocity should be high and consequent. So this is about the equal pressure drop method. The modification of equal pressure drop method is equal friction method. In this method, the frictional pressure drop per unit length of the duct is maintained constant throughout the duct system. In this method, frictional pressure drop per unit length is maintained constant. Knowing the airflow rate and the velocity in the main duct, the size and frictional loss are determined from the chart. The friction chart are used to determine the size. If we are having the friction loss value and the velocity, so we will get easily. This method of sizing duct automatically reduces the air velocity in the direction of flow. The method is generally recommended because it is simplistic. If an equal friction design has a mixture of a short and long run of duct, the shortest duct will need to considerable amount of damping. This is a drawback of a equal friction design. The damping should be provided because of large noise and because of it having higher velocity, so it will produce more noise. So the damping is provided. It should be provided. So that is the only drawback of this method. But this method is widely used in the app and the industry. So now we will see one numerical. Numerical is in the duct system. The cross section of the main duct is such that the width is always twice the depth. The total quantity of air entering A is 690 meter cube per minute and the static pressure at A is 18 mm of water. A branch 0.9 meter broad and 0.6 meter deep is laid off at B for the length of 45 meter. This discharges at atmospheric pressure and there is a loss of zero point 0.5 velocity ahead at the conversion piece. Another branch is at C is so designed that the discharge 120 meter cube per minute of air. So we have to calculate the dimension of three section of the main duct, designing on the basis of uniform pressure drop, and condition is given that neglect the velocity changes in the main duct and assume that the discharge pressure at D is atmospheric. So the value of friction factor taken as 0.0055. So solving the numerical, given data is written down, we know that when the velocity changes in the main duct AD are neglected and the static pressure at A must be equal to pressure loss due to friction between A and D. So we can apply the Bernoulli's equation or just simply have the equal pressure drop method where the pressure drop between the AB, BC and other section is same. So it's basically taken as PSA, static pressure at point A, which is 18 mm of water. The total length of duct is LAP plus LPC plus LCD. Three main sections are calculated and then total length we get as 105 meter. Then pressure drop per meter length of the duct AD. First we have taken the whole duct main duct AD. So pressure drop per unit length is 18 upon 105 is 0.17 mm of water. This pressure drop should be maintained constant throughout all ducts and all branches. Now for the duct AB, B1 is the depth of duct AB and A1 is the width of duct AB, which is twice of B1. And cross section area is 2B1 square. Now weighted perimeter is 6B1. Now hydraulic mean depth M is B1 upon 3. Then velocity of air in the duct AB is Q upon A, which is 5.75 upon B1 square meter per second. Now velocity pressure in duct AB is PVAB, which is V upon 4.04 whole raised to square. Then it is 2 upon V1 raised to 4. We got the PV pressure velocity. Now pressure loss due to friction in the duct AB is given by formula F into LAB upon M into PV at AB. Now put all the values. We will get 0.99 upon B1 raised to 5. It is our final equation for this branch AB denoted by 1. Since the pressure drop per unit length is 0.17 mm of water, therefore total pressure loss due to friction in AB is, so we have to multiply by length because pressure drop per unit length we are having 0.17 mm of water. So pressure drop in AB is 0.17 multiplied by 30, which is 5.1 mm of water. So equating the term, we will get B1 dimension of B1. So B1 we get as 0.194 meter. So twice the length, which is A, which is 1.44 meter. Now dimension. Now we are having the dimension of AB. Now we have to calculate for BC. First of all, let us find out the quantity of air flowing through B. The area we are having 0.54 meter square. Now weighted perimeter of a duct B is 3 meter and the hydraulic mean depth M is A upon P, which is 0.18 meter. Pressure loss due to friction in B. Pressure loss per friction in B is 1.375 PV. Pressure loss at conversion piece is given in question as 0.5 into pressure loss at B. So we got the value pressure loss at B is equals to, we have to add conversion pins and that loss 1.375 plus 0.5 P VP, which is 1.875 PV at the section of BV. Now pressure loss at B is static pressure at A minus pressure loss in section AB. So we will get pressure at B is 12.9 mm of water. Equating the term, we will get pressure loss at BB is equal to 6.88 mm of water. And we know that the velocity of air B we can calculate with the formula VB is equal to 4.04 root, because this comes from the formula PVB is equals to V upon 4.04 whole square, which is dynamic pressure formula. So from that we can get velocity at section BE, which is 630 meter per minute. Now quantity of air flowing through the duct B is equals to A into VB, so we get 340 meter cube per minute. Now quantity of air flowing through BC, so we have to minus it. So from AB minus BE we get quantity of air into BC, which is 350 meter cube per minute. Now we are having flow rate in the BC and area which is A2B2, which is 2B square. Now weighted perimeter is 6B2 and 2 is equals to B2 upon 3. Now velocity at BC is equals to Q upon A, which is 175 upon B2 square. We can also return it to form of meter per second, which is 2.92 upon B2 square meter per second. A velocity pressure in the duct BC, PVBC is equals to VB square upon VB upon 4.04 whole square. After the putting the all values, we get PFBC is equal to FL upon M PVBC. Now, finally, since the pressure drop is 0.17, we are having, so just multiply by length, so we get pressure loss in section BC, which is 7.65. Now, after the putting the value, we will get value of B, which is 0.05. B square is 0.005. Now taking the B, which is 0.55 meter, and A2 is double of B2, which is 1.1 meter. So we got the dimension of the section BC. Now we have to get the dimension of duct CD, our main duct, which is CD. So taking the dimension and cross section, weighted perimeter is also calculated. Now similarly as the previous, we get the quantity of air QCD is equals to QBC minus QCF. QCF we are given in the question, which is 120. So 350 minus 120 is 230 meter cube per minute. Now velocity at CD is equals to Q upon A, which is 1.92 upon B3 square meter per second. Put into velocity pressure formula. Now get the value of velocity. Then we have to put the values into pressure loss due to friction loss formula. PFCD is equals to F into L upon M multiplied by PB at CD. Putting the value, we get the 0.112 upon B3 raised to 5 mm of water. Also, pressure loss due to friction in the duct CD is 0.17 into 30. 30 is the length of section CD. The total pressure loss is 5.1 mm of water in the section CD. So equating the term, PFCD is we got 5.1. Now put the equating with the 0.112 divided by B3 raised to 5. We get the B3 value is 0.466 meter and A3 as 0.932 meter. So that's all. That is the numerical we have solved based on the duct design method. So more numerical if you want, then you can comment and we will get more numerical and solve. And if you want notes, so you can refer the RS Kurme book. From there you can solve various numerical based on these two topics. Thank you.